接下来呢是 DNV 的 Dr. Uday Deshpande，他是 CTO Chief Technology Officer，他要分享的题目呢就是刚才康乐哥提到的，一直提到的 Inverter。好，Inverter Test System for Validation and Production，它是预录的影片。Dr. Uday Deshpande。
Hello everyone, my name is Uday Deshpande. I'm the CTO of DNV Electronics and I welcome you to this presentation. We're going to talk specifically about testing EV inverters and using emulators in particular, and we're going to talk a little bit about reducing the cost of test without compromising safety, quality, or test coverage. Now, this presentation was prepared together with our partner from NI, Brandon Bryce. However, I will be making this presentation for you today. Who are we? So DNV has been in the testing business for over 20 years. We've started historically testing ICE components, specifically starters, alternators, and then have grown from there to testing hybrid and electric powertrain systems. We also test emulator-based, offer emulator-based testing products specifically for electric motor emulators and DC emulators. In 2017, DNV was acquired by Motor Car Parts of America, and we now operate as an independently held company under them the last 5 years. Over the range of the various industries that you see over here, we manufacture test solutions across the various industries for both motor as well as power electronics components. And then we offer products that support laboratory testing, production line testing, as well as aftermarket maintenance, repair, and so on. As I mentioned, we work very closely with NI. Our partner NI is, as you guys are probably well aware, they are a $1.3 billion company with a strong presence in over 40 countries with 35,000 customers worldwide. And the focus of NI is to equip engineers and enterprise with systems that accelerate their productivity, innovation, and discovery. More critically, then, they are very specifically focused on software-connected solutions. And if you take a look at what they offer across the board within engineering expertise, their modular hardware platforms that they offer, on top of that you've got application and development software, all of which that again covers the spectrum from research, design, validation, production, deployment, and maintenance. And has been around for many years. I'm sure quite familiar with all of them. And then their analytics and test operations through the use of Optimal Plus and System Link provide a really good way of handling and managing not just the data, but then generating insights from the testing that is done. If you then look further, NI has been focused on getting more solution specific and then provide tailored and application specific solutions in the broad areas of interest for EV application, some specifically inverter test system, EV battery test systems, and ADAS record and replay. So NI has the hardware software tool chain along with the systems approach, and so we work with NI, and we'll talk about this a little bit more, to provide more specifically power level solutions that are used for inverter testing. Now, if you take a look at what's happening in the industry in this space, what are the customer expectations? The customer expectations historically, you've got a HIL, a hardware in the loop type testing, where the test unit, the device under test, is the controller or the motor control unit, if you will. And then the control algorithm software allows you to debug your code in real hardware. And what you have in order to do that is that everything else, the powertrain, that is motor, power electronics, things like vehicle dynamics, road loads, various drive cycles, etc., they're all simulated in real time, so that the control hardware experiences real-time behavior. But then once you have the controller hardware done, the next step is to actually test the power hardware. And so the power hardware essentially now manifests itself into what we call power hardware in the loop. And this is where, as we show over here, the emulator now comes into play. So what we have is the device under test now is the actual inverter, the power stage, as well as the controller that we just talked about earlier. And then the way to test it is now a power device that allows the inverter to actually be tested at power levels. We can use the same interface in terms of the models that we use for the motor. We can use a lot of the old setups, use the models for vehicle dynamics, road load, drive cycles, etc. And then transfer from signal level testing that we did on the controller to power level testing that we can do on the inverter. Now, once you have done that and you validated the inverter, so you can think about the emulator, and we'll talk about this a little bit more, almost like an electronic dyno. The whole setup can actually go to a real dyno where you can test all the way up to a electric axle, in which case it's not just the motor and the inverter, but it's the motor, the inverter, and the gearbox tested in a more conventional dynamometer setting. So now you're emulating the battery and the road load, etc., but you are testing the real motor. And I apologize, I just realized typo there. So with this setup, the customer really wants to be able to cover the complete range of testing, right? All the regulatory standards need to be satisfied. Operations ideally are seamless across the operations data and controls, whether you're testing the controller or you're testing the full powertrain or the e-axle. And then the solution should be able to support the various protocols, formats, and be easy to use. And so this allows a company to be able to test the entire inverter, not just at the inverter level, but also then finally all the way up to powertrain level. Okay. So as we then start looking at this, now since we're talking specifically about the inverter, we're going to focus on that. So what are some of the trends in the inverters? Right? So the inverter then can truly be called the heart and the soul, right? So that is the real intelligent component. If you think about it, no matter what action has to be taken by the drivetrain, the inverter drives the motor behavior and the responses from everything, even from steering systems, ADAS systems, and so on. Anything that has to happen at the wheels comes ultimately through the inverter. If you then think about in terms of general development cycles, typically this tends to be asynchronous, meaning the pace at which a inverter prototype might be ready is not necessarily the same as the motor prototype. So the relative maturing of the two components are not the same. Plus the controls may need to be developed even before the inverter hardware is available. So this asynchronous behavior requires some special consideration. Further technology trends in miniaturization, going to high number of phases, higher frequencies, use of wide bandgap devices, higher voltage buses, implications to EMC, diagnostics and health monitoring, impact to DC link capacitor technology. All of these things require a mechanism that allows us to test the inverter without loss of fidelity. Meaning we have to be able to test the inverter and ensure all of its behavior is appropriate, even as we may not have some of the other downstream components like the motors or the gearboxes and such available to test. So then, if you take a look at the design lifecycle, and specifically if you think in terms of the test lifecycle, you see a continuum. You see a continuum that on the left-hand side is a pure software testing, and then right-hand side is pure physical testing. So your left-hand side, you're in design. As you start getting from design into real world, you go through maybe simulation, emulation, you get into lab, test cell, rig-based testing, and so on. And so, when you're in the software testing, things like model in the loop, software in the loop tend to be lower cost, they're faster. You can do a lot of what-if scenarios really quickly, but fidelity may be lower, or you increase the simulation emulation complexity, right? As you start moving to the right, the flexibility might decrease. You test a physical hardware, then you have no idea where that hardware is in the distribution across the manufacturing spectrum, for example. It's more real, but you can test within the capability of that physical hardware, and you don't necessarily know everything else that might be happening within the broader manufacturing spread. Till when you get to the field test, it's a much higher fidelity. Everything is real, but obviously that's more expensive, more time consuming, especially if you need to get statistically significant testing done. Then the number of test units start increasing, and obviously along with it, time and cost. So what you have is that if you start trying to shift left, so you start doing more and more testing to the left in this continuum, you can do scenario testing lot better. You have a flexibility to test different technologies even. You're not as dependent on real system availability. You can actually accelerate the testing. And if you guys are familiar with software testing, you're probably very, very familiar with the idea of shifting left and moving things more into unit testing as much as you can. Now, in the middle, what we didn't talk about, and we touched upon it briefly, are the hardware in the loop and power hardware in the loop. So what they do now is they present an additional capability that increases the flexibility of testing, gives you some more capabilities of test coverage without having to, with an increasing realism, but without having to go to full rig-based testing or a full unit in the field testing. So as you move to the right, what you have, while the cost and risk, time to fix all of, and the effort, all of it starts becoming higher. And if you're able to distribute that risk across the entire testing spectrum, what you find is that you can get a fairly high level of confidence coming into the final field test with almost a 90-95% coverage, right? And that then is the goal for all of this stuff that we want to do on inverter testing. And the reason for the backup is so that we understand, what the thought process is in terms of how we approach the idea of inverter testing to include controller testing. Now, this obviously is made possible by the very well-known V diagram. So you've got the system decomposition on the left-hand side, and then the recomposition integration on the right-hand side. And what you find is that, in principle, if you guys have heard of virtual engineering, virtual prototyping, then a lot of this work can be done in the virtual, semi-virtual simulation world, to minimize the number of real hardware testing that you have to do. And what you see here is the tool chain that we have between NI, and I'm going to introduce Opal RT as well in the mix over here. We'll talk about them more in just a second, but we can run through the full gamut of testing, all the way from decomposition verification to solution verification. So we've already covered this. Customers look for being able to go across the spectrum from controller hardware to power hardware to dyno, so that we can get the maximum coverage that's possible. Now, we talk about how do we do this. So let's look at the traction inverter test, especially if we start talking about the controller testing. And in the controller testing, we talked about this before. All the elements are modeled, the motors are modeled, the inverter power hardware is a model, any vehicle dynamics, road load cycles, all of them are modeled. And this typically we have the NI hardware and software, along with Opal RT hardware and real-time capabilities that are brought to play to provide the ability to test the controller. So what you'll find is just about everything else other than the controller is simulated, and then you have the real-time computer or the real-time simulator that you see up top right. That helps to interface with the DUT. The DUT thinks it's actually running a real inverter and the real motor, so you have real-time testing of the controller hardware and software without requiring any real hardware for anything else. Now, the operative word over here is real-time models, because we want to make sure that the latencies and the responsiveness of the system is replicated so that the DUT is truly senses that it's testing the real system. So high-speed emulation is very, very critical. If you then go to beyond that and you say that, okay, great, we've tested the controller, we need to test the inverter. Now, if you take a look at this, we've got more or less the same setup that we had before, but now we've added the DNV electronics emulator systems into the mix. So we take the setup that we have. Now we can not worry about the controller hardware at all and go straight into inverter testing, assuming that the customer had other means of developing the controller hardware. So some of the controller testing software development can also be done at the P-Hill level. So you don't maybe necessarily have to do it at the C-Hill level or Signal Hill level if you don't want to. So if you look at the previous slide and this slide, what you'll find is now what you have is that the motor is emulated, but the motor is emulated such that, let's say, for example, you get the effect of the real back EMF as well as the position that's fed to the inverter, and then the emulator actually provides the means for being able to absorb real power, so that the real current flows out of the inverter into the motor that is emulated in this case. So now you're testing the inverter at full power, and so you can do all the tests that you would typically want to do between performance testing, torque speed profiles, efficiency mapping, loss characterization, controls tuning, controls optimization. You can also do temperature testing, temperature studies. You can do everything that you want to do on the inverter because you're able to do this power. Now, you can also do fault injection. So both resolver faults, for example, temperature sensor faults, for example, current sensor faults, a lot of faults, phase-to-phase faults, phase-to-ground shorts, open phases, all of these tests that you want to do in order to establish the robustness of your design can all be done using the emulator. So let's take a little deeper look at power hardware in the loop. So what you see over here is the motor emulator in the middle. This basically runs the motor model in real time. So you have got really, really high speed, maybe low microseconds into high nanosecond type loop cycles to get the most out of the real-time emulation of the motor, so that the inverter is convinced that it's actually testing a real motor. As you see, rotor position, things like motor temperatures can all be fed into the inverter. The controller, the real-time controller, in this case shown the NI Pixie chassis, provides the motor torque command to the traction inverter, speed command to the motor emulator, and what you have is really no different than how you would set it up and run on a dyno, right? So some people call this the e-dyno. Now what you have is that the DC emulator that you see over here can be used to represent a battery. It can do a battery emulation, so that if you want to start seeing the droops and the voltage behavior of a battery, you can use the DC emulator. Now, a couple of things over here. You see this green arrow called power circulation. Now, this is something that is unique to DNV, the way we control this. So because of the power circulation that is done within the DC, what we have is that the inverter and the emulator is fed from the same DC bus, and the power circulates within the DC. So typically, you only need to feed a very small percentage of the total power from the grid. So typically 10 to 15% or so is what is expected to be fed from the grid, which allows the emulator to be effectively what you see over there. That is a 19-inch rack, about a 4 foot by 4 foot base cross section is what you're looking at space-wise. And for the channel shown over here, this is up to 275 kilowatt, 800 volt system. But for a 275 kilowatt, 800 volt system, you're only providing about 35 kilowatts of power from the grid. Like I said, you can have just that much power in the system, or you have this DC emulator. The DC emulator by itself is a 500 volt or a 960 volt bidirectional DC power supply with some really fast full power um, bandwidth. So actually 20 kilohertz bandwidth all the way up to 100 kilowatt at 800 volts, 960 volts. So it gives some really unique capabilities for testing DC systems, like for example aircraft systems that have got multiple DC sources and various electromechanical actuators. All of this system can be mimicked using series of DC emulators, and that allows you to study everything from system resonances and frequency sweeps, voltage sweeps that you might want to do on a DC power system. So the combination of this actually presents a very strong capability of testing the traction inverter pretty much all at full vehicle level. So we talked about the real-time motor model, but like I showed you in a previous slide, it's very easy to incorporate real-time vehicle dynamics models, road load models, drive cycles, etc. Then if you take this system and you start having, let's say, thermal chambers, for example, you have a fault injection unit that allows you to do, like I described, both power level faults and sensor level faults, along with appropriate power quality measurements, real-time test automation software, if you need more DACs for more temperature measurements and so on. All of that could be incorporated. And once you have all of this in here, we actually call it a inverter test system as well. We call it power hardware in the loop over here just to prevent some confusion between the signal level inverter test and the power level inverter test. So moving on from there, now that hopefully you have an understanding of what the P-Hill looks like, when you get into emulator-based testing, again, the key is real-time and FPGA-based simulation. So at the bare minimum, we are talking about the motor models. Now, the motor models typically can be a couple of different ways. You can do flux table lookup, tables based of flux FD and FQ. Relatively simple. You get saturation, but you don't get higher order effects like spatial harmonics and so on. Or you can generate 3D models from tools like ANSYS finite element tools or JMAG finite element tools, and that allow you to give you a higher fidelity motor model that includes spatial harmonic behavior and so on. You can incorporate mechanical models, mechanical component models, like half shafts and stuff. If you want to do that, you can get full vehicle dynamic models, drive cycles. So you name it, all of them could be run in the real-time system. So as far as the inverter is concerned, it feels like it's running a motor that is basically behaving like the drivetrain, running the wheels. And so you effectively are testing at vehicle level in the lab. So emulator-based testing gives you a tremendous amount of flexibility. So for example, you want to study motor behavior, right? So simply change the model, right? You're looking at motor designs. You're not sure if there is one motor design better than the other. No problem. Even if you're running this at on the emulator, you can just replace the motor model, and now you can study the behavior of a slightly different motor. So let's say you want to test out a different slot pole combination. No problem. Little bit more involved to do, but you can also study manufacturing behavior, right? So variations due to manufacturing, parameter variations, all of these can be studied depending on how sensitive the parameter variation effects are. We can start studying those effects as well, so that you can do your controls tuning, and you can do your controls, even algorithms tuning, to reflect the ability to handle the manufacturing tolerance variations that you might expect. So the emulator-based testing truly gives you a degree of flexibility that you cannot get on a traditional dyno-based testing that is used for testing inverters. So trying to then summarize. So if you take a look at that, when we start looking at DNV and NI along with O-polarity, what do you get? So like I said, you can emulate characteristics of permanent magnet synchronous machines, induction motors, full power in all 4 quadrants. I've not mentioned 4 quadrants. The current loop rates at 80 kilohertz, and then less than one microsecond latency, so that you get a fairly sufficient model accuracy for testing the inverters. Just a note, our subsequent generation solutions will have higher loop rates than what we are showing today, what we have today, just to increase the fidelity of what you can study in the motor, which allow you to study higher speed machines and so on. Using the NI toolchain, one obviously gives a well-established series of hardware and software that is robust and well understood and appreciated in the marketplace. Presents a much stronger and more robust solution that we can come forward with, along with the added flexibility and knowledge of the real-time models and systems, the real-time systems capability that Opal brings to the table. So we get much better models that we can run low latency deterministic communication that ensures that we minimize the error due to emulation. You can accelerate development from various sources, sim power systems, PSIM, multisim. You can take those models to speed up development. If you've already done simulation, you can use those models convert them to real-time mode and then run them on these P-Hill systems. The DC power circulation that we talked about, helps reduce operating costs. Facility requirements are significantly reduced, and then you get a compact design. Now, you might have noticed that these emulators are on casters, so you can actually move them around. Now, while we talked about inverter testing, one of the things that the DC-DC converter can do, so I said it's a bidirectional DC-DC converter. It actually allows you to be able to test things like onboard chargers, DC-DC converters, and so on as well. So if you have a system that is designed for some high-level inverter testing, and so let's say you've got 2 DC inverters because you need that 200 kilowatts of power, or for example, then those 2 DC emulators can be removed from the inverter testing and reconfigured to do, let's say, a DC-DC converter testing, right? So with the scalable I/O and the power electronics that we have both from NI, from Opal, and from DNV, you can actually foolproof future-proof your test systems, so that you don't have to you're not starting from scratch. So, for example, our emulators channels can be paralleled up to 1 megawatt. So if you start having really large motor systems up to 1 megawatt, you can have two channel EMEs, and you've got ability to test a 1 megawatt inverter. And then with this, with all of this and the internal expertise that we have, it certainly will reduce the time for first test, and then time to help speed up your overall testing. So like I said, the emulator covers from development testing. We talked about controls development, etc. So now if you want to start doing inverter durability testing, you can do this durability testing with the emulator as well. So being very commonly used, we find that the EME offers a very repeatable system to allow you to do everything from reliability type testing, or just straight durability testing, temperature testing, any kind of testing that you want to do as part of your development cycle. So at the end of the day, you get decreased product development cost because you're able to test early and catch your mistakes early at smaller component levels, so you can replace and fix things faster. You end up with improved products and decreased time to market, right? And so this is all done with a combination of simulation and emulation that allows you to test your design strategies if you want to. You can expand the quality of test cases. Again, like since there's a largely simulation emulation element, you can do a lot of what-if scenarios without worrying about things getting damaged or loss of hardware, or the concern about an inability to represent a variability that you run into in real life. You can identify systems earlier, which helps to both fix problems quicker and reduce time to market. At the design validation phase, you can start doing real-time simulation. And in fact, one of the things can be done is rapid testing during requirements decomposition, for example. So if you really want to do some quick checks on whether this requirement makes sense, you might be able to use this system to do some some quick testing. And then it's full power testing without being in a vehicle, and in many cases without all the real vehicle components. So we really aim to drive test agility across the full development cycle for complex systems. So with that, I end my presentation. I hope you found it useful. I'm happy to provide more specific information on our emulators and testing with emulators. I've got some other presentations that I've done in the past. If people are interested in digging a little deeper, my email is over there. If you're interested from a more commercial side of things, the sales team's email is there. And then we also have Brandon's email in case people are interested in contacting NI directly as well. So thank you very much for your attention. I hope this was useful. And while we can't take questions live, I'm happy to answer any questions I get by emails, or if the organizers are collecting questions during the presentation, then I'm happy to receive those list of questions and I'll answer them as fast as I can. Thank you very much. Have a good rest of your conference.
Okay, thank you, Dr. Uday Deshpande. That was a presentation for Brendan. Now, moving on, the next topic is about powertrain